So now we will discuss Fourier transform. What is a Fourier transform? So Fourier transform in continuous time domain first. So Fourier basis we have uk is equal to e to the power j 2 pi ft. What is e to the power j 2 pi ft? E to the power j 2 pi ft is a complex sinusoidal signal which is basically cos 2 pi ft, the real part, plus j sin 2 pi ft, the imaginary part. Now this is the Fourier basis. Now using this Fourier basis in the analysis formula, we can analyze the signal. So we can break down the signal and we can make a spectral representation of the signal xt by doing that. So xt after a Fourier transform shall change to xf. This is the Fourier coefficient, and this Fourier coefficient can be given by the analysis formula. xf is equal to the inner product of the basis and the signal xt normalized by mod uk square. Now the thing is, the Fourier basis is a complete signal, so the mod uk square is essentially an integral of the signal square magnitude that gives 1, and this upper part is uk. The inner product is defined as uk conjugate t xt dt and integration over the total signal definition interval. We suppose the signal is a continuous time signal, so it is defined from minus infinity to plus infinity. So it's minus infinity to plus infinity. So uk conjugate t. So this is a complex function. So a conjugate of the complex function is just a minus j. So ultimately we have xt times e to the power minus j 2 pi ft dt, and that is the definition of the Fourier transform of x. That is xf is equal to integration minus infinity to plus infinity xt times e to the power minus j 2 pi ft dt. Now this is the basis of Fourier. This is the Fourier transform. Now if there is a Fourier transform, there should be an inverse Fourier transform. But we first want to understand what happens in the Fourier transform. A Fourier transform transforms the signal in the time domain. So there is a time domain representation of the signal, something like this. xt varies over time. And this time domain signal is transformed into a frequency domain signal with a certain discrete variation in the frequency domain, where it varies over the frequency, and that is xf. So this is a discretization from the time domain to the frequency domain with certain frequency spectrum. So what xf gives us, the Fourier transform gives us the oscillatory behavior of the signal over the frequency f that is contained in the signal in the frequency domain. And if we take a look closely at xf, the modulus of xf square, that specifically gives us this integration. If we do a modulus square on this integration, we actually get integration minus infinity to infinity mod of xt squared dt e to the power minus j 2 pi ft times 2 mod over this and then dt. And this is basically the energy of the signal at that particular frequency f. So we are saying that this xf is the spectrum of the signal in the frequency domain. This xf gives the measure of the oscillatory behavior of the signal at the frequency x contained in the signal. So basically this inner product gives us a measure of the similarity between the signal x and the basis, Fourier basis uk. And the third point is the modulus of xf squared is giving us the energy of the signal at the particular frequency f. These are some of the key properties, or what we say, some of the key ideas that we get from the Fourier transform. And then there is a theorem, Parseval's relation. So this Parseval's relation holds true for a finite energy signal. So Parseval's relation or Parseval's formula or Parseval's theorem, whatever we say, true for a finite energy signal where a signal xt has an energy Ex is equal to integration minus infinity to plus infinity mod xt whole square dt. That's the energy of a signal, definition of the energy of a signal. And the Parseval's relation says that the Fourier transform follows the law of conservation of energy. So when we transform the signal from time domain to frequency domain, what happens is the energy is conserved also in the frequency domain. In that case, the energy of the signal xf should be EF or EXF is equal to integration minus infinity plus infinity modulus of xf square df. And we say this energy and this energy are equal, and that gives us the Parseval's relationship. So this Parseval's relationship holds true, and the Fourier transform conserves the energy. So this gives us a distribution of the global energy of the signal in the frequency spectrum. So that is the basic idea of the Fourier transform. And then if we have an analysis, this is our analysis formula, then we must have a synthesis. If we can have an analysis, we can have a synthesis. So how can we synthesize the same signal from its spectrum, from its frequency spectrum? We can use these Fourier coefficients to get the signal back, and there what the idea of synthesis comes. So the synthesis, on the other hand, is xt is equal to what? xf times uk, integration over the df. So what is uk? The Fourier basis that we initially take, that is integration minus infinity to plus infinity xf e to the power j2 pi ft df. So this particular integration gives us the signal, an approximation of the signal back. So this is our synthesis formula, which is called the inverse Fourier transform. If this is the Fourier transform, and then this is the inverse Fourier transform in the continuous time domain. So this is literally the inverse Fourier transform that gives us the signal back. That means we basically take a weighted linear combination of the Fourier basis, and that weighted linear combination of the Fourier basis weighted by xf, which is the Fourier coefficient, is basically the signal xt. That's the idea of the synthesis. That's the statement behind the synthesis. So this is the basic definition and points related to the Fourier transform. The next moment is all about the properties of Fourier transform. So we have to focus on 10 main properties, PHE, 10 main properties of Fourier transform. So globally we define that xt is the signal in continuous time domain which has a Fourier transform xf. So xt has a Fourier transform xf. So what are the 10 main properties of Fourier transform? 1 is the area property. 2 is the conjugate symmetry property. 3 is the delay property. 4 is the modulation property. 5 is the duality property. 6 is scaling. 7 is convolution. 8 correlation. 9 periodization. 10 sampling. These are the 10 main properties of Fourier transform that we need to focus on. Now what is the area property? The Fourier transform is xf. At the value of frequency f is equal to 0 is specifically the area of the signal, that is xt dt. So the area of the signal is equal to x0. Now on this particular property, I want to remind of certain thing, that the area has to be a finite value only when we can have a defined x0. That means the area of the signal needs to be a finite case. This brings me to the Dirichlet's conditions. So the Dirichlet's conditions are these. Dirichlet's conditions. So definitely it's a general name, but Dirichlet's conditions. So what is the Dirichlet's condition says? if the signal is defined over an interval minus infinity to plus infinity, then the area of the signal, that is this, must be a finite value. That is the first condition. Second condition, the signal has finite number of discontinuities inside that interval. Finite number of discontinuities inside that interval minus infinity to plus infinity. And the third condition, the signal has finite number of maximum and minimum values inside that interval. So in the same interval, the signal has a finite area. In the same interval, it has finite number of discontinuities, and also in that same interval, it has finite number of extremum values, maximum and minimum values. So if a signal supports all these as true, then it holds the Dirichlet's conditions as true, then only that signal can have a Fourier transform, and then only we can apply the Fourier transform and we can arrive at these properties of Fourier transform. So the first property of the Fourier transform is the area property, which we say at frequency f is equal to 0, the Fourier transform of the signal basically gives out the area of the signal. Then the second property is a conjugate symmetry property. Fourier transform is a conjugate symmetric function. That means the conjugate of the Fourier transform xf is equal to the Fourier transform xf. Okay, so that's why if we do a Fourier transform of a particular signal, let's say a rectangular signal is there. So this is a rectangular signal with an amplitude a and the time period t. We define it as xt is equal to a rect t of t, and the Fourier transform of this signal shall give us a sync signal like this, which is basically xf is equal to at sync pi ft, which is basically at sin pi ft by pi ft. Now this looks like this in theory, but in practice when we do a Fourier transform of the signal, we get some graph like this, where we get something like this and something like this. So we can get something like this here and something like this here. Now this doubling of the thing, that is at some same sort of a distance, is basically a reflection of the conjugate symmetry property of the Fourier transform. That's the idea. The third property that we have to focus on is the delay property. So if we introduce a time delay in the signal, what happens to the Fourier transform? So the xt minus a delay of capital T has a Fourier transform of xf times e to the power minus j2 pi f capital T. So the spectrum is always multiplied with this complex sinusoid governed by this delay factor t, which we have taken in the time domain. So this is how the Fourier transform changes. After this, there is a modulation property. That means if we do the same multiplication in the time domain, what happens? If we do xt multiplied with e to the power j2 pi f0t, or let's say f0 is a modulating frequency, then in the frequency domain, the frequency is shifted by f0 or the f0, that is the modulating frequency. So there is a frequency shift in the frequency domain. That is a modulation property, this particular thing. And the duality property is, if we take a Fourier transform of the Fourier transform, so if we do a Fourier transform of the Fourier transform itself, xf, we get the signal in a mirror image, x minus t. So we get the mirror image of the signal. That's the duality property. Scaling property is, if we take a scaling in the time domain, this is an alpha scaling factor. So in the frequency domain, it is also scaled as 1 by alpha x f by alpha, something like this. Okay, so these are the first 6 very basic properties, and the last 4 properties are big enough, so I will move on just expanding over those properties. So last 4 properties, that is convolution, correlation, periodization and sampling. So one by one. first property, that is convolution. What is convolution? So convolution of a signal, that is zt is equal to xt convolution yt, can be defined as integration minus infinity to plus infinity x tau y t minus tau d tau. So this is a huge integration in the time domain. But if you take the frequency domain representation, zf is equal to xf times yf. It is just a simple product. So if xt has a frequency domain xf, yt has a frequency domain yf, then the product xf and yf is basically the convolution's own frequency domain. So if you do a inverse Fourier transform, you get the zt. So convolution becomes far easier in this setup. In the Fourier transform is just a product, and just inverse Fourier transform will give the convolution result, because in general this thing yt minus tau, so we have to invert the signal and we have to offset the signal to a certain extent, and then taking the inverting and offsetting the signal, we have to make a running multiplication over all the xt's, and then make a running sum over all the xt's in the discrete scenario. So we are doing a lot of operations. So first of all, taking the two signals in a matrix, then inverting the signal in another matrix, offsetting the signal by some scalar, and then running it over all the matrix elements of x and summing it up. It's a lot of operations which results in a lot of computation. So that's not so easy. But if you take Fourier domain representation of xt and yt, is just one product, one mathematical operation, and that gives you the zf. And inverse Fourier transform gives you back the convolution of the signal. So this is a very nice convolution property. And then the correlation property is basically, what is a correlation? As I initially said, a correlation is inner product. So inner products can be thought of as a correlation. So in some way, this correlation zt, how do we correlate xt and yt? So it's some sort of an inner product, and it can be expressed as x conjugate tau y t plus tau d tau, and integration minus infinity to plus infinity. And if we take in the Fourier domain, that is the frequency domain, this is just x conjugate f times yf. That is the correlation property. But also I forgot to say one thing. Okay, this is the correlation property. I want to add some other thing to the convolution property. So we are doing a convolution only in the time domain, and we see that thing. So zt is equal to xt convolution yt has a frequency domain case, where zf is equal to just xf and yf multiplied. If we just multiply the signals in the time domain, what happens? So zt is equal to xt times yt. Then in the frequency domain, zf should be equal to a convolution of xf and yf. Now how do we expand this definition of convolution? This is basically integration minus infinity to plus infinity x nu y f minus nu d nu. So that's basically the duality property of the Fourier transform. If we take a convolution in the time domain, Fourier transform is just a product. If we take a product in the time domain, Fourier transform is also a convolution in that case. So that was the convolution property. Then I said the correlation property, that is correlation between the signals is defined as x conjugate tau yt plus tau d tau integration. So we have zf, the Fourier transform is just the Fourier transform of xf's conjugate times the yf, that is just another product. So it becomes easier in the Fourier domain. And then the last two properties is about the periodization and sampling. So what is the periodization property of Fourier transform? So let's talk about that. So periodization refers to that a signal xt, suppose a signal gt is there, which has with a Fourier transform gf. Now we periodize the signal gt in the time domain. So if we do the periodization, so we can express it as xt is equal to summation g t minus kt, k is equal to minus infinity to plus infinity. So this is the periodic representation of the signal as a periodized signal. So some signal was there like this, and after periodization this signal became something like this in the time domain. So it should have some Fourier transform, and how will the Fourier transform change? That's what we want to see. So after periodizing the signal in the time domain, the Fourier transform also changes something like this. Xf is equal to, if we take the period as the fundamental period as t, so the fundamental frequency should be 1 by t, okay, summation g of k by t, that is the harmonic frequencies, with the Dirac delta function del of f minus k by t, k is equal to minus infinity to plus infinity, or whatever the variation of k was. So this basically is the Fourier transform represented. So initially the Fourier transform was just g of, but what is g of k by t, del of f minus k by t? This del of f minus k by t is actually an impulse train, so which is centered at the harmonic frequency. So 1 by t is the fundamental frequency, and integer multiples of the fundamental frequencies is basically the harmonic frequency. So the periodic signal is xt with harmonic frequencies k by t. So the del of f minus k by t is the impulse function centered at the harmonic frequency. What is an impulse function? Good question. What is an impulse function? Del t is defined as 1 when t is equal to 0 and 0 otherwise. But actually it's not del, it's del n, because it's mostly a discrete thing. So an impulse is a discrete thing. So it's like this. Where n is equal to 0, it is a value, but for other cases it is 0. So when we say del f minus k by t, so it is an impulse train only specified on those particular values of frequency, and g k by t basically attenuates the amplitude of the impulse, so it results into some sort of impulse train sampled signal in the frequency domain. So that is the periodization property. And when we go on to scaling, we see that when we go on to sampling, for sampling we see that to discretize the signal in the time domain, we basically multiply the signal with an impulse train. So we basically sample the signal in the time domain. So this is some sort of frequency domain sampling of the same signal. Now sampling property is basically the same, is the opposite of this basically. So we are saying we have a time domain signal xt and we are sampling this signal to xst. Now what is the sampling? So sampling is basically we are multiplying the signal with an impulse train. So we are multiplying the signal xt with the impulse train, which is a summation of delta t minus kt. So this is an impulse train where k is equal to anything, minus infinity to plus infinity, or whatever interval we define. So xst is equal to this. This means we are multiplying the signal with an impulse train. So the signal is something like this, and the impulse train is basically over a period of t like this. And when we multiply the signal and the impulse train, something results into some sort of attenuated impulses at those very portions where the signal appears with some value. So something like this. So that is the basic idea of sampling. So we are essentially discretizing the signal, and that is what sampling is doing. Now what happens to the Fourier domain? What happens in the frequency domain is, okay, so we can actually write it as xkt of del of t minus kt, where k is equal to minus infinity to plus infinity. In the frequency domain, xf becomes, this is as 1 by t summation xsf becomes xf minus k by t. K is equal to minus infinity to plus infinity. So if we look at it clearly, when we said what is periodization, we said xt is equal to g of t minus kt summation like this. And now we are saying in the frequency domain also, the xf was the Fourier transform for xt. Now for xst, the Fourier transform looks like something like this, 1 by t times summation xf minus k by t, which very much looks like the periodization definition, but that was a definition in the time domain. So essentially is what happening in the frequency domain, there is a periodization of the signal. So if we sample the signal, the Fourier transform is periodized in the frequency domain. That's the property. So this is the sampling property. Fourier transform is periodized in the frequency domain. And that ends all the properties. So all the 10 properties discussed for Fourier transform.